In this video, I want to talk about another type of induction called strong induction. And it's strong in the way, it's not that it can prove more. In fact, it can be shown, it's a little bit beyond the scope of this course, but it can be shown that all types of induction are essentially the same. If you can prove something using one type of induction, you can prove it using any of the others. So it's not strong that way, but it's strong in that we're making a stronger assumption than with regular mathematical induction. So basically, the idea is that we're going to do a base case again for our least element in our domain. And for our assumption, instead of assuming that for some k, that if pk is true, then pk plus 1 is true, we're going to assume that pk is true and all values less than k as well. So pm is true, pm plus 1 is true, all the way up to pk is true. So we're going to assume that if they're true, then pk plus 1 is true. So this is our assumption here. And if that holds, then we've proven our open sentence is true for all elements in our domain set here. And I want to make a quick note. A lot of times in strong induction, you might have to do more than one. It's not quite a base case, and I say here more than one base case. I'm going to put this in quotation marks. But it might come out to look a lot like a base case. Because for a lot of times strong induction is useful, it'll be times when sequences are defined recursively, which means one element of a sequence is defined by the previous elements of the sequence. So you might have to do a few extra cases, as we'll see going forward. So I think the best way to talk about strong induction is to do an example. So let's do one. In fact, we're going to do an example using the Fibonacci numbers. This is one of the most famous sequences in mathematics. Basically, you start with the elements 1 and 1. They're the first and second elements of the sequence. So you can write these out. And then we get the next element. So for all n 3 or bigger, we get Fn by taking the sum of the previous two elements. So here is F1, here is F2, they're given to you. F3 is going to be the sum of the previous two. So 1 plus 1 is 2. F4, the previous two, 2 plus 1 is 3. F5, 3 plus 2 is 5. F6, 5 plus 3 is 8. F7, 8 plus 5 is 13. We'll do one more. F8, 13 plus 8 is 21. And we can keep going like that forever. This is called the Fibonacci sequence, or the Fibonacci numbers. So we want to show in this sequence that the nth term is always less than 2 to the power of n for any n. So let's go ahead and do this. All right, so the proof is going to be by induction, by strong induction, in fact. So let's tell people we're doing this. Okay. Well, our base case is when n equals 1. That is the least element in our set. Our set is indeed the natural numbers, and the least element of the natural numbers is 1. So, well, F1, here's F1 here, the first element of the sequence, is F1 less than 2 to the 1. I'll put a little question mark over that because that's what we're checking. But f1 is 1. 2 to the 1 is, of course, 2. This is true. We like that. So our base case is indeed complete. Okay, let's do our inductive case now. Now notice we're going to assume something different. So assume for some k in our domain that indeed that fi is less than 2 to the I, and it's going to be for all I that's between our least element and that element k. So we're thinking of this isn't necessarily 1, this is our least element. So remember, what we're assuming is f1 is less than 2 to the 1, f2 is less than 2 to the 2, f3 is less than 2 to the 3, all the way to fk is less than 2 to the k. So we're assuming all of those things. And we want to use that. We want to show that fk plus 1, the next one up from k, is less than 2 to the k plus 1. That's what we want to show. And we have to be a little bit careful here. So remember, so note, just a little reminder, that the Fibonacci numbers are defined as the sum of the previous two numbers for all values 3 and greater. And the reason it's 3 and greater is because, well, we need 2 below it to use this formula to define the next term in the sequence. So f1 and f2 have to be given to us for this to make sense. So they are. So let's write this down. This is just a reminder that was given to us in the question. f1 equals 1 and f2 also equals 1. And that's going to be important when we do our induction, because this formula can only apply for values 3 and greater. So for smaller values, we might have to do some special cases. Okay, so let's go ahead. Let's consider fk plus 1. So we have to think of a way of using our inductive hypothesis. Remember, our inductive hypothesis tells us things about terms in the sequence less than fk plus 1. So fk minus 1, fk minus 2, anything less than that. But luckily, we have this definition of how to build a term from its two previous. So I can use the definition of the Fibonacci numbers to say this is fk plus fk minus 1. The kth term in the Fibonacci sequence plus the k minus 1th term in the Fibonacci sequence gives me the k plus 1th term in the Fibonacci sequence. And now, using that definition, I can see how I can use my inductive hypothesis. I know that each of these is less than 2 to the index. So let's do that. This is going to be less than 2 to the k plus 2 to the k minus 1. And this is by the inductive hypothesis. But we have to be a little bit careful, because remember that we can only use this when k plus 1 is 3 or greater. For k plus 1 greater than or equal to 3, which is the same thing as saying that k is greater than or equal to 2. So this means, and we'll do this afterwards, this means that we have to handle the case when k equals 1 separately. Okay, so let's finish this off, the nice general argument. We'll worry about those cases at the beginning afterwards. Remember, we want to show that this is indeed less than 2 to the k plus 1. So let's think about how we can show this. Well, looking at this, I'm thinking, well, if I can think of this in terms of 2 to the k minus 1, I might be able to figure out how to write this above as this expression here, or something close to it. So I'm going to think about this as 2 to the 2 times 2 to the k minus 1. So I'm thinking of 2 to the k plus 1 as 2 to the 2 times 2 to the k minus 1. Now what I can do is I can factor out a 2 to the k minus 1 from both of these terms. So this is the same thing as, well, if I factor out a 2 to the k minus 1, in fact, I'll put that second. I'll factor it out on the right. Then what do I have left over? I have a 2 to the 1 in the first term and a 1 in the second term. So you can check that this is the same thing here. So 2 to the k minus 1 times 2 is 2 to the k, and 2 to the k minus 1 times 1 is, of course, 2 to the k minus 1. So these are the same expression. I want to show that this is less than 2 to the k plus 1, which is 4 times 2 to the k minus 1. So here I have 3 times 2 to the k minus 1, and that obviously is less than 4 times 2 to the k minus 1. So using that idea there, we have that fk minus 1, if we follow our inequalities, it's less than 2 to the k plus 2 to the k minus 1, which is the same as 3 times 2 to the k minus 1, but that is obviously less than 4 times 2 to the k minus 1, which is, if you simplify this, I should have an equals here actually. Change this to an equals. This is the same thing as 2 to the k plus 1. So we showed, if we follow the inequalities, f sub k plus 1 is less than 2 to the k plus 1. Since we only have equals and less than signs in there, this guy on the left is less than the guy on the right, if this was written out in one long line. So we're done, except for we have to deal with the case when k equals 1. So special case is when k equals 1. So when k equals 1, well, what's f2? f2, in fact, I'll write it like this first. f1 plus 1, because we're thinking of this guy as our k. Well, we want to show that that's less than 2 to the k plus 1. But remember, in this special case, k is indeed 1. So this is f2 is less than 2 squared. But obviously, f2, we have that term. f2 is 1. That's the second term in our sequence, and that is obviously less than 4. So we're good to go. So we've done our base case. We've done our inductive case for all values when k is 2 or greater, and then we had that special case assuming that k equals 1. We showed that it's true in that case as well. So we've done our base case and our inductive case. The result is true. For all n in our domain. And that's how strong induction works. I will make a quick note here. Some people like to think about the special cases kind of like base cases. So think like extra base cases. So we had to do an extra base case in this scenario. And the way to think about it is, I'm going to scroll back up here. There we go. So our Fibonacci sequence is defined by 2 previous terms to get a term. So each term is defined by the 2 previous terms. So you're going to need 2 base/special cases. We had 1 base case, 1 special case. So you can think about it like that. You're going to have to do 2 cases separately in order to do this strong induction. Let's look at another example. Here's our next example. We have the sequence. I tell you a couple of terms. Here's A0, A1, A2, and I tell you how to make the nth term in the sequence for all n 3 or greater. It's the term before it, the term before that added together, and then added with 2 copies of the term even before that. So an is the sum of an minus 1, an minus 2, and 2 an minus 3. So what I want you to do is guess a non-recursive formula for an and then prove that it's indeed true. So my suggestion to you guys right now is to calculate a few elements of this sequence. So calculate, we have A0, A1, A2. Calculate maybe A3, A4, A5, A6, maybe A7 as well. Keep going like that until you get a feel for what's going on in the sequence. And then see if you can guess a formula that's not recursive that can define an. So you're not building it out of the sequence's previous element. So pause the video and try it now yourself. Okay, now that we're back. Well, we know A0 is 1, A1 is 2, A2 is 4. Let's calculate A3. So A3 is going to be A2 plus A1 plus 2 copies of A0. So that's going to be, well, A2 is 4, A1 is 2, and 2 copies of A0, well, A0 is 1. So that's 4 plus 2 plus 2 times 1 is 2 is 8. So A3 is 8. Let's calculate A4. So that's going to be 8 plus 4 plus 2 times 2. 8 plus 4 plus 2 times 2. So that is, of course, you can check, 16. Let's do one more, then I think we can take a guess at what this formula is going to be. A5 is going to be 16 plus 8 plus 2 times 4. So that's 16 plus 8 is 32. So this is A0, this is A1, A2, A3, A4, A5. So looking at these, it looks like to get from 1 term in the sequence to the next, you just multiply by 2. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So a good conjecture for this formula, and that's what we're going to prove, our conjecture, is that an is just 2 to the power n. So this is what we're going to prove using strong induction. So let's go ahead and do it. So proof by strong induction. We need a base case. Let's do that first. And our base case, our least element this time, is indeed 0. And I should note that for an, where n is, of course, in the natural numbers, including 0, so the whole numbers. So our base case is when n equals 0. Okay. Well, is a0 equal to 2 to the 0? Well, a0 is 1. 2 to the 0 is 1. That's true. It's true. For our base case, we like that. All right. Let's do our inductive case now. So remember, we need to assume for some value k in our domain, which is the whole numbers or the natural numbers starting at 0, that pk is true and pi is true for all values I less than k. So let's write that down. So we're going to assume for some k in our domain, and remember our domain this time is the natural numbers including 0, that I could say something like a0 equals 2 to the 0, and a1 equals 2 to the 1, and a2 equals 2 to the 2, all the way up to a k equals 2 to the k. But instead of saying that, I'm just going to write down that for i's that are between, should be a 0 here actually, between 0 and k, that ai equals 2 to the I. So that's saying the same thing, right? So this is saying that starting at 0, a0 equals 2 to the 0, and then keep going up until you get to k. So a1 equals 2 to the 1, a2 equals 2 to the 2, a3 equals 3 to the 2 to the 3, all the way up to ak equals 2 to the k. So we're assuming all of those. There's an and in between everything that I was saying. And we want to show that a k plus 1 equals 2 to the k plus 1. So let's consider a k plus 1. And remember, we had a formula that recursively defined what this k plus 1th term was. It was the term before it plus the term before that plus 2 copies, 3 terms before it. So we have the k plus 1th term is the sum of the kth term, the k minus 1th term, and 2 times the k minus 2th term, or k minus 2nd term. Okay. But remember, this only holds when our index is greater than or equal to 3, which means k is greater than or equal to 2. But this isn't our least element. Our least element is 0. So we need special cases for when k is 0 and k is 1. But let's deal with them after the fact. Let's do the general k plus 1 is greater than 3 cases first. So let's use our inductive hypothesis. Remember, we're assuming that this formula holds for everything k and smaller, for all indices k and smaller. Here are indices k and smaller, k, k minus 1, k minus 2, so we can use our inductive hypothesis. So this equals 2 to the k plus 2 to the k minus 1 plus 2 times 2 to the k minus 2. Because remember, that's what we're assuming, that ai equals 2 to the I for all values of I between 0 and k. Okay, let's clean this up a little bit. So 2 times 2 to the k minus 2, well, we can think of this as 2 to the 1 times 2 to the k minus 2. So this is the same as 2 to the k plus 2 to the k minus 1 plus 2 to the 1 plus k minus 2 is k minus 1. And hey, look at this. We can keep going here. Let's get a little more room. There we are. So I have 2 copies of 2 to the k minus 1, so let's add them together, plus 2 copies of 2 to the k minus 1. Here's one, there's the other. We have 2 copies. But just like before, I can think of this as 2 to the 1. So I'll use my exponent rules. This is 2 to the k plus 2 to the 1 times 2 to the k minus 1. 1 plus k minus 1 is k. And using that same logic, we have 2 copies of 2 to the k. And that's 2 to the 1 times 2 to the k. So 1 plus k is k plus 1. So we've done it. We've shown that a k plus 1 equals, we have equals all the way down, equals 2 to the k plus 1. So we've proved it besides our special cases. So, all right, let's do our special cases now. So when k equals 0, well, that means if k equals 0, then we need to check that it's true for a to the 0 plus 1. So that's a1. Well, that is indeed 2, which is 2 to the 1. That's good. And when k equals 1, then 1 plus 1 is 2, so a2 is 4, which is 2 to the 1 plus 1, which is 2 squared. And so that case is good. So we did our base case. We did our inductive cases, including those special cases we needed to do. So we're good to go. We can just say the following. So by strong induction, the result is proved. And we're finished. So again, remember, we had 3 terms that were defined by themselves, or you think of the recursive sequence is a sequence that requires 3 previous elements to construct the next element. So I needed to have 3 base/special cases. And if you think about it, I did A0, and then my special cases were the next 2, A1 and A2. I had to check them separately because my formula didn't apply to them. Let's look at one more example. This one, on its face, looks a little more difficult, but not really. The algebra will be slightly harder, but not much harder. So let me remind you what the Fibonacci numbers are. We know F1 is 1, F2 is 1, and Fn is the sum of the n minus 1th term and the n minus 2nd term when n is greater than or equal to 3. So that's the Fibonacci sequence, same sequence as from our first example. We're asked to show that the nth Fibonacci number is given by this, which looks like a kind of disgusting formula, but not really. And I will clue you in to something, that these guys here in our brackets, these are the golden ratios. And I don't want to go into too much detail about what they mean, but they're very intricately related to the Fibonacci numbers. And if you're interested more in that idea, it's a good idea to just Google it, put in golden ratio, read about it a little bit. It is a quite interesting topic. So this is a good opportunity for you guys to practice. This example is a little more challenging, algebraically more than anything, but give it a go. So pause the video now, work out your base case when n equals 1, because remember, the Fibonacci numbers are defined, its implicit domain is when n is indeed a natural number. So figure out the base case, and then do the inductive case afterwards using strong induction. And I want to make a quick note. I'd think to use strong induction here based on the fact that this is a recursively defined sequence. So I need 2 terms before a term to define the next term. So because that's the fact, regular induction is not very useful for me, but strong induction absolutely is. And there are other times where strong induction comes in handy. Basically, any time that you can take an object and break it into smaller constituent parts, that is the time that you want to use strong induction, or strong induction would be handy. Anyway, for now, let's try this example. I would say pause the video, try at least the base case yourself, and then see if that goes well, then do the inductive case afterwards. Okay, now that you're back, let's go ahead and give this a go. Our base case is when n equals 1. Let's do this in black. N equals 1. So I know that f1 is 1. Let's figure out what this is. 1 over root 5 times 1 plus root 5 squared to the 1. I won't write to the 1 because anything to the 1 is just itself. Minus 1 minus root 5 over 2 to the 1. So let's simplify this. This is the same thing as saying 1 over root 5 times 1 plus root 5. And I'll kind of distribute this negative across to the denominator. So we'll get minus 1 minus a minus root 5, which is plus a root 5, over 2. And that is in my square brackets there, which I'll drop next anyway. So this is 1 over root 5. And here we have 1 minus 1 is 0. Root 5 plus root 5 is 2 root 5. So we have 2 root 5 over 2. And hey, look, our 2's cancel. And we're left with root 5 over root 5. Our root 5's cancel. So all we have is indeed 1 over 1, which is indeed 1. So f1 equals 1. This expression here, when n equals 1, is 1. So our base case is proved. Let's do our inductive case. So, for our inductive case, we're assuming for some arbitrary k in our domain set, and our domain set is the natural numbers in this case, that for all values I between our least element and that value k that we picked, that fi indeed equals this 1 plus root 5 over 2 to the I minus 1 minus root 5 over 2 to the I, and I need to divide by root 5, so I'll put 1 over root 5 at the start. Okay, so if you haven't tried it from here, it's a good idea to pause the video and try this yourself. Remember, you want to show that this is true for k plus 1. We're assuming it's true for all values from 1 to k inclusive. We want to show it's true for k plus 1. So remember, we know that each term in the Fibonacci sequence, except for the first two, are defined as the sum of the previous two terms, so we can use that knowledge. And we have our inductive hypothesis that we can use as well. So give that a go. All right, now that we're back, let's consider fk plus 1. I'm going to figure out a way to use my inductive hypothesis to turn this into fi terms that are k or less, and I can just use the definition of the Fibonacci numbers to do that. I know that fk plus 1 is just the sum of the two terms before it, the kth Fibonacci number and the k minus 1th Fibonacci number. Okay, so we did that, but remember, this is when k plus 1 is greater than or equal to 3, which is the same thing as saying k actually is greater than or equal to 2. So we have a special case of k equals 1 at the end. So our special case is k equals 1. So we're just going to have to check that by ourselves afterwards. Okay, let's keep going. Well, let's use our inductive hypothesis. We're assuming that our formula holds for index k and less, so let's use it. So this must equal 1 over root 5 times 1 plus root 5 over 2 to the k minus 1 minus root 5 over 2 to the k. So that is our fk inductive hypothesis. Let's do it for k plus 1. 1 over root 5 times 1 plus root 5 over 2 to the k minus 1 minus 1 plus root 5 over 2 to the k minus 1. Oh, that should be a minus there. I'm going to change this, indeed, to a minus. And that is using our inductive hypothesis on fk plus 1. We used our inductive hypothesis, so let's tell people we did that by our inductive hypothesis. Now, if this result is true, and I will tell you indeed it is, of course it is, that's why we're doing it as an example, in order to get from this step here to our final step, which is just this expression here, but k plus 1 replaced instead of i's, it's just a matter of algebra. So we just have to do the correct algebra to simplify this. So let's go ahead and do it. I have a common factor of 1 over root 5 at the start of both terms, so I might as well factor that out first. So this is the same thing as 1 over root 5 times, and maybe just to make things a little easier so we can see what's going on a little clearer, I'm going to call 1 plus root 5 over 2, I'm going to call that a plus, since there's a plus in the middle there. And you can imagine what I'm going to call this term here. I'm going to call this a minus, since there's a minus there. So I'm just going to rewrite this as a plus to the k minus a minus to the k. And then we factor out that 1 over root 5, so we have plus a plus to the k minus 1 minus a minus to the k minus 1. And this is just a little bit of notation. Remember, this a plus just stands for this 1 plus root 5 over 2, and this a minus stands for 1 minus root 5 over 2. That's just some ad hoc notation I made on the fly, just to make it a little bit easier to write down and see what's going on. So let's collect our like terms, and eventually I'll replace the a plus and a minus by what they mean. But let's rewrite this with the a pluses and a minuses next to each other, just so it's a little easier to see. So this is 1 over root 5 times, well, this will be a plus to the k plus a plus to the k minus 1. There's this guy, there's this guy. And then the a minuses are both subtracted, so I'm going to collect their like terms, and I'm going to put them inside a set of brackets themselves. So we have here a minus to the k plus a minus to the k minus 1. And you can check this is the same thing, right? Minus, so it's negative a minus to the k. Here it is here. And we have negative a minus to the k minus 1. Here it is here. So let's simplify each of these expressions. In fact, maybe let me do this a little color-coded so it's a little easier to see. Let's make these brackets green. And I'm going to put a set of brackets here. Let's make these brackets blue. Group the a pluses and a minuses together. Okay. So let's simplify things a little bit. We have this 1 over root 5 hanging out. That'll simplify a little bit later. No problem. So I see a common factor of a plus to the k minus 1 in both of these terms. I'm going to factor that out. So this is a plus, oh, my blue bracket. This is a plus to the k minus 1 times, well, we still have an a plus here, and here we have a plus 1. So that's what's going on there. So I factored out an a plus to the k minus 1. You can check if you multiply back. Here we have a plus to the k minus 1 times a plus. So we have k a pluses first. And then we have a plus to the k minus 1 times 1 is a plus to the k minus 1, of course. So that takes care of the first term here. Let's do that second term. And it's going to be the same thing, right? The only thing that looks different is here we had a plus, here we had a minus. So this becomes a minus to the k minus 1 times a minus plus 1. Okay. So we did that, and it might be kind of easier to put our values for a plus and a minus back in, so we can start simplifying this a little more. And again, this is just a big old algebraic simplification. So this becomes 1 plus root 5 over 2 to the k minus 1 times 1 plus root 5 over 2 plus 1 minus 1 minus root 5 all over 2 to the k minus 1 times 1 minus root 5 over 2 plus 1. Okay. So let's close our end bracket there. So let's simplify this a little bit. We still have our 1 over root 5 here. Let's simplify inside of these brackets. So this is going to be, this is the same as 2 over 2. So this is going to be 3 plus root 5 over 2. So we still have this 1 plus root 5 over 2, the k minus 1. And this is going to be 3 plus root 5 over 2 minus, this again is going to be the same 1 minus root 5 over 2 to the k minus 1, and this simplifies to 3 minus root 5 over 2. Just remember thinking about this guy as 2 over 2 and then adding it. Because they have the same denominators, you can just add the expressions and you're good to go. Close our bracket. Okay. Now, you could think that it might be hard to see how we can get, let me just write something down here. Remember, what we want is 1 over root 5 times 1 plus root 5 over 2 to the k plus 1 minus 1 minus root 5 over 2 to the k minus 1. That's what we're looking for. That's what we want to show. And it might be kind of hard to see that this expression actually equals this, or how to go about this. But remember, we know where we want to go. So let's use a little bit of thought here. So we have k minus 1, 1 plus root 5 over 2's. We need 2 more. And those 2 more have to come from here. So if we can show that, let me just do this here. If we can show, need to show that indeed 1 plus root 5 over 2 squared is 3 plus root 5 over 2, then we're done. And similarly here, instead of a plus, we just have a minus, so maybe I'll make this a plus minus either way. So if we can show that that is true, then we're done. This would equal 1 plus root 5 squared. 1 plus root 5 over 2 squared. And then we have k minus 1 plus another 2 is k plus 1 of these a pluses. And same thing here. If this was 1 minus root 5 over 2 squared, then we'd have k minus 1 of them times 2 more. So that would be k plus 1 of them, and we'd be good to go. So let's see if we can show that result. In fact, that's not too bad. We just need to do a little bit of checking. So I'm going to leave that as a little bit of an exercise for you guys. Just a little small algebraic exercise. Show that this is indeed true. If you can show that that's true, we're good to go. Then we get this is 1 plus root 5, or sorry, 1 over root 5. This is 1 plus root 5 over 2. That's our a plus to the k minus 1. Doing the little exercise there, this is the same as 1 plus root 5 over 2 squared minus 1 minus root 5 over 2 to the k minus 1 times 1 minus root 5 over 2 squared. And again, this exercise shows you why this is the case. And the reason that I came up with it is I know where I want to go. I need 2 more a pluses, 2 more a minuses, so these must equal a plus squared and a minus squared. And you just need to check that in order to show it. And then, well, in fact, I don't need another line here. We're just done. We can use our rules for multiplication with powers, so we just add our powers, and we get 1 over root 5 times, well, a plus to the k plus 1 minus a minus to the k. This should be, sorry, a plus 1 here. I wrote a minus before, but that should be a k plus 1. Okay, so we're almost done. We just need to do that special case of when k equals 1, which is f2. So we know f2 equals 1. We just need to show that 1 over root 5 times 1 plus root 5 over 2 squared, maybe I'll put a square bracket here, minus 1 minus root 5 over 2 squared, that indeed also equals 1. Again, just a little algebraic exercise, but we kind of know how to do it because we know from the previous exercise that I gave you that this is 3 plus root 5 over 2. This is 3 minus root 5 over 2. So this is 1 over root 5 times 3 plus root 5 over 2 minus 3 minus root 5 over 2. And again, this is by that exercise from before. And if we simplify that, we get 1 over root 5. And we have the same denominator here, so we get 3 plus root 5 minus 3 minus a minus root 5, so plus a root 5, all over 2, which is indeed 1 over root 5, plus 3 and minus 3 cancel out. So we have 2 root 5 over 2, and just like before, our root 5s cancel, our 2's cancel, and this again is 1. So we've done it. We've done our base case, we did our inductive case, which meant we had to do a special case when that formula didn't hold. We just had to check it by itself. But we're good to go. Everything worked out. So we can say, by strong induction, the result is proved. So again, this argument wasn't particularly different than the other ones. The only thing that was a little more challenging was the amount of algebraic manipulation we had to do. The ideas were all the same, except for that big chunk of algebra in the middle. So hopefully this all made sense. You will definitely need to do a few more examples by yourself to make sure that you have this down. And again, just make sure that when you're doing the inductive hypothesis, you're assuming that for some k, that the result holds for all values k and below to your least element. Remember, that's your strong inductive hypothesis. So it's not that much different from induction, except you get to assume a little bit more.